Hi and welcome to part 3 of my Unlocking the Mysteries of Brushless Motors video series, where I'm going to answer the question, how can you choose a motor for your RC speed car? I'm going to show how, amazingly, it's possible to calculate the torque and power curve of a motor that you don't even own, and from that, the car's entire potential performance. Along the way, we'll also see whether a lower kV motor will provide more torque. And at the end of the video, I'm going to share 2 pieces of good news with you. We're going to start with a blank torque versus speed plot and then build up a curve for a 660 kV motor running on 3 cells and 45 amps of phase current. Just as a bit of a reminder from part 2, this is the shape of curve we're looking to create. So we're going to create a constant torque region, then hit the base speed, and then go through the declining torque region down to the no load speed. So we're going to build all that up with some basic data that's readily available for any motor really. So starting with the constant torque region, we're going to calculate the torque with this formula that I got from this book called Motors for Makers. It's simple, which I like, and it's just the phase current, which in our case is 45 amps, minus the idle current, which I've estimated to be 2 amps. It's usually quite low and almost insignificant really, divided by the kV value of the motor in radians per second per volt, so a slightly different unit to what we've used so far, but I'll show how that gets converted now. So this is the motor data that I'm going to use, but actually I'm going to cheat slightly. I'm going to use a measured kV value that I got from just running the motor with no load on, measuring the speed and then calculating it manually. I measured it to be 620 kV, you see, so slightly different to the quoted value. So here we go, 45 amps minus 2 amps idle current, divided by my 620 kV value times 0.1047, which is the correction value to go from RPM per volt to radians per second per volt, and that equals 0.66 newton meters. So going back to our blank plot, we're going to add the constant torque region on, just a straight line there. And you might remember in part 2 I did show that as the RPM gets higher, torque does tend to start reducing due to eddy current losses, and you can calculate that, but you need some really detailed motor parameters which aren't really readily available. But if you work within the manufacturer's operating range of the motor in terms of the number of cells you're running on, then I don't think the losses should be that significant. I did find that I was running into that problem because I was operating outside the manufacturer stated range, like I was going above 8 cells, whereas that was stated to be the maximum for that motor. So I think we're all right with our straight line for now anyway. So what are we going to do next? Well, next we've got to work out the no load speed. So that's very simple. Again, it's just the voltage applied times the kV value. Again, I'm going to use my 620 kV, kind of from the motor data there, but I did actually measure it. And that comes out at 6,882 RPM. It might look like I'm using a low voltage for this, but that's because I did the physical test on a storage charged battery, so I've used the voltage of that battery for that. So what does that give us then? That gives us our point on the x-axis where the torque reduces to 0 and the motor doesn't spin any faster, so I've plotted that there. Next we're going to work out the base speed point, which will be somewhere along this line. To do that, we've got to work out the voltage drop that comes from the voltage trying to push current through the motor, and that can be calculated from the current times the resistance of the motor phase multiplied by 2, because at any point in time the speed controller is putting current through 2 of the motor's 3 phases. The internal resistance of the motor is actually a readily available piece of data. So again, I could have used this exact data, but I decided to use a measured value which I got from the motor just with a multimeter, and it came out at 25 milliohms, so it was quite different to this. So it's better to measure it if you have the motor. If you haven't got the motor, you can just use the quoted value. So I'm going to put my 45 amps in, multiplied by 0.025, which is my 25 milliohms divided by 1000, multiplied by 2 for the two phases, and that equals 2.25 volts, which obviously isn't the base speed. To get the base speed, we've got to take the no load speed and then take off the voltage drop that we just calculated, multiply the by the kV value again. So it's pretty simple really. So yeah, so 6,882 RPM, subtract the 2.25 volts times 620 RPM per volt kV value, and that equals 5,487 RPM. So going back to our curve, we're going to add the base speed point we've just calculated, draw a nice straight line between the two of those, and then that is our approximation of what we think the curve's going to be for a 660 kV motor running on 3 cells at 45 amps. So now let's compare that with the measured data. So there you go, it's actually very close to the measured data. The agreement's really good. Certainly good enough to use as an approximation. I mean, we're slightly above the measured data because we haven't considered factors like voltage sag, saturation or eddy current losses as measured earlier, but I think this is certainly good enough to use as an approximation to put in some other calculations going forwards to do some more estimations of our speed car performance. When I first did this, I couldn't believe how accurate the prediction could be, and I started thinking about how I can make use of it in my speed car development. Let's have a look at what I came up with. This is an extract from one of my previous videos called The Science of Speed. So we're going to apply a torque to our wheel. That generates a tractive force which tries to push the car forwards, and that's equal to motor torque times the gear ratio times the wheel radius. I've got to keep reminding myself to mention the gear ratio because my car doesn't have one, it's just 1 because it's direct drive, but most other people's cars will have a gear ratio, so that's why I'm mentioning it. So that pushes against the ground. Then there's a friction force with the surface that the car's resting on. And that actually works to push the car forwards and allows it to accelerate. Of course, if the tractive force is greater than the maximum friction that the surface can support, then the friction force will stop going up. But up until that point, the friction equals the tractive force. As the car accelerates, it's going to start experiencing air resistance. And I showed how that can be calculated in my Science of Speed video. And as long as that friction force is greater than the air resistance force, the car's going to accelerate. But eventually that difference becomes 0 and a constant speed is reached. What if there was a way of working all of these forces out for our speed car? Because if we could do that, then surely we could get some estimate of what the car's performance is going to be. Unfortunately, there is a way of doing it. I've created a spreadsheet that brings all of that together, so let's go and have a look at that now. Here it is. Here's my speed car template spreadsheet set up in Google Sheets. The yellow cells are where the user puts in inputs. Red cells are ones where we can make some small adjustments if needed. So it starts with the basic car specifications like wheel diameter, frontal area, a drag coefficient estimate, then looking at its mass and mass distribution. So I'm suggesting 10 kilograms, 60% on the front for this car. And you can put in your downforce to drag ratio. So based on how much drag you've got, it will then calculate how much downforce to apply on the front and the rear wheels. You've then got other basics like the gear ratio, quantity of motors, and the number of cells you're planning to run the car on. It does assume that all 4 wheels, well, it's a 4-wheel vehicle for starters, and that all 4 wheels are the same diameter, and that the power goes to all 4 of those wheels. So then we've got these other inputs here are the air resistance parameters, powertrain efficiency estimate, wheel slip estimate, friction coefficient with the road estimate. Then we put in our motor parameters, which are readily available, as I showed before, off their data sheets. So those go in here. We've got the kV, phase resistance, and what current you're going to apply to the motor phase through the test. Then the spreadsheet calculates the aerodynamic forces, the motor torque and the tractive forces, then the friction forces, and then it takes all of those together to calculate the acceleration and then the powertrain side of it, so what motor RPM range you're in and whether you're within the battery current limits. So we'll come back to that in a sec, but let's work through the graphs that I've generated. So we've got the motor torque versus RPM plot that we just created manually for that 3-cell 45 amp test. The spreadsheet does that automatically. This sheet compares that motor torque and tractive force, available per axle. So that's that blue curve there. If you look at the yellow curve, that's the friction force we've got available at the rear. So that shows that the tractive force is actually higher than the friction force, so we could actually easily wheel spin the rear tyres of this car. But at the front we actually have more friction force available because of that extra weight on the front of the car. But the way I've set this up is that I'll assume that we're driving the car, so we're using the limit of traction of either the front or the rear wheels as the limiting amount of force that we can apply. So if you look at this one here, this is the resultant total force available to accelerate the car. So that's the equivalent to the tractive force per axle times 2. And you can see that it's just double the friction force available at the rear axle, because that's the one that's limiting our traction. Up to the point here where the tractive force available starts tailing off because our motor torque is tailing off. So that's why it gradually increases, because the friction's going up, and then goes down because we're losing torque from the motor. So where does that leave us speed-wise? Well, this is the resistance force, so this is like our aerodynamic drag. You can see how it massively goes, well, it starts going up faster as you go at a higher speed. And our tractive force tails off at about, about 170 miles an hour. So the maximum speed the car could reach is at this point here, so that would be about 190 miles an hour. But as we saw in my Science of Speed video, we've got to worry about how much distance it's going to take to get up to that speed, because we can only see the car for a certain distance. So we can see that to hit that 190 mile an hour mark, well, it doesn't actually get to 190, say 180, it's going to take nearly 600 meters to get there, and that's assuming we're accelerating at the limit of traction the whole time. So we can use that information to help us. And then finally I've got a plot of battery current versus speed and electrical power, so we can check where we are against our limits of our powertrain. Talking of which, we can also do that in the calculation sheet itself. So I've got it set up, so say for example I had a 200 amp powertrain limit, it's going to highlight the cells in red where it goes above that, so we can see that above 130 miles an hour we're going to be into that limit. And then also in terms of the motor RPM, if we had a 20,000 RPM limit on the motor, we can see we're in a green region here because that's at or above our base speed. So it goes into that region at 170, but then if the car did ever get to 220 miles an hour, then we'd actually be at our RPM limit for the motor. Although we've seen from the plots, it won't get that fast anyway. So you're probably wondering, does this actually agree with real life? Well, I put in the values for my Cone speed car that I ran at Rossa Round 1 and Rossa Round 3 last year. Well, it's actually the Round 1 version because it's got the 1850 kV motors. And this is the speed versus distance plot that's correct. Oh, sorry, speed versus time plot. Speed versus distance is this plot, and it thinks I can get a maximum speed of about 120 miles an hour with it, absolutely topped out. And I did actually achieve a speed of 107 miles an hour with this car, so not that different from what this is predicting. And there are significant differences with what this is predicting though, in that, you know, when I logged the data from that run, I showed I was only accelerating at about 0.2 to 0.5 g, whereas with a coefficient of friction of 1, which this spreadsheet assumes, it's assuming an acceleration rate of 1 g effectively, initially at least. And also, I wasn't managing the power smoothly through the run because it's difficult, even with a throttle delay. So I think that's why there is a difference between, you know, the theoretical result and the practical result. And you're always going to get that. The idea of it is to use it as a tool to help guide your powertrain choices. So now I'm going to show a couple more examples to illustrate how this could be useful. Starting with my actual results for my beast car that I'm expecting based on my powertrain measurements. So this torque curve, I've got it set up so I can actually add in a bit of a correction factor to allow for the eddy current losses I experienced. So that predicts the full torque curve of my car running on 10 cells. And then if I look at the speed versus distance plot, it's predicting that I should be able to get over 200 miles an hour just about within 600 meters of distance, which is quite reassuring. To me, it shows that I haven't made too bad a decision with the motors that I chose originally, and the car has got 200 mile an hour potential. Then going back to the question that I asked at the start, does a motor with lower kV have more torque? Let's have a quick look at the torque curve predicted here for the 660 kV motor, and we're up around 1.3 Newton meters peak. This is the curve for the 400 kV motor, the same motor but a different version of it, and it's only about half of what the 660 kV one is, and you're probably wondering why that is, and that is mainly because the maximum current you can push through this motor, it's less than half of what the high kV motor is. And because of that, you know, in that formula we saw at the start where the torque generated is related to the current, the torque you generate just isn't anything like as good. And of course it signs off earlier as well because it's got that lower kV value. So this is even with 12 cells instead of 10 cells of that plot we just looked at. And what the implication of that is that it will never reach 200 miles an hour. And I mean, in 600 meters it'll just about get to 160 miles an hour theoretical speed. So again, that reassures me that I've chosen the right motors for my beast car project. And you know, just it's something to bear in mind that a lower kV motor, you might think it'll have more torque, but that's only if you can put the same current through it as a high kV motor, which you probably can't because it's going to have more turns on it, and so because of that they tend to have to use thinner wire which has a lower current limit. Here's a bit of an experiment I did where I decided to change my beast car from having 4 in-wheel motors to 2 TP motors, similar to what people tend to be using on speed cars that tend to do pretty well. So I've put a gear ratio of 3 on the car. I've got 2 motors there running on 10 cells, and I've got TP motors 4080 10 cell specification, and I've put in the values from their website, and I'm running it at a maximum phase current of 200 amps, whereas it can actually achieve 300 amps. So let's see what that gives. So we've got the torque curve here, so its maximum torque is over 1 Newton meter, so that's pretty high, considering I've got the gear ratio of 3 on there as well. So what we're going to see here is that unsurprisingly we're easily able to wheel spin on both the front and the rear axles of my car. So you know, we're limited in tractive force then by the rear axle traction. So that's shown by that curve there, and then it tails off at it looks about 240 miles an hour, so it carries on for quite a while there. And then in terms of speed versus distance, it's with that combination it's looking pretty similar actually in terms of how much distance it takes to get to 200 miles an hour. So just before 600 meters we're getting to that speed. So yeah, it just shows that the powertrain that I've got in the Beast car, it's not that dissimilar to a typical like dual TP motor type powertrain. Although I suppose it is limited by how much traction I've got on the rear of the car. So if I was able to get more downforce on the rear earlier, then maybe that would help it go faster. Next we're going to look at an FTX Banzai that I got for my son as a beginner's speedrun car. So I've put it in exactly how we've got it set up in terms of the powertrain. So it's running on 3 cells, quite a cheap surplus hobby 5900 kV motor. And I've assumed that we've put quite an aerodynamic body shell on it with a drag coefficient of 0.3, maybe slightly optimistically there. And I've assumed no downforce effects. So my motor torque curve, it signs off very early actually, as you can see there, and as a result we're going to see not a very high top speed. So it looks like it can maybe get just over 60 miles an hour, maybe pushing 75 miles an hour. But I mean, my son, he really wants to get to 100 miles an hour and potentially get his first Rosser hat. So what would he have to change to get that? Let's have a look. So if we were to change the number of cells, if I put that to 4 cells, firstly we should just have a quick check of the RPM limit. Oh yes, so we're already hitting the 50,000 RPM limit of that motor. It's going red at about 70 miles an hour, so we're going to have to change the gear ratio as well. So let's change that to say 4.5. Let's see how that's affected. Has it pushed it up to 100? No, it hasn't. Well, let's push that up to 100 and then we'll see where we are with it. So gear ratio 4 I think is going to be needed for that. Is that right? Yeah, so that's hitting the RPM limit after 100 miles an hour there. But let's see what we've got then. So we've pushed the torque curve where it gets to the base speed up the RPM range a bit by adding more voltage, and we're working around where the friction force is, so that's probably not too bad a place to be, although the motor does sign off quite early on. And as a result, you know, we're going to be accelerating much less through this period here. We'll probably see that in the speed versus distance plot. Yeah, we can see that it's certainly starting to labour as it goes over 100 miles an hour, but it does show that maybe it has got 100 mile an hour potential if you could keep the car on the ground pointing the right way and the insides of the car aren't falling apart, which is another factor. Yeah, so you know, it shows how you can tweak the parameters to give yourself some ideas of what you could try to get your car to go faster. Today we've seen how it's possible to calculate the torque curve of a motor and then combine it with aerodynamics and friction calculations to simulate a speed run virtually. This could take some of the guesswork out of configuring a new car or developing one you already have. You can vary the car's weight, aerodynamics, motor, gearing and see what the effect is, all from the comfort of your own home. And now I have 2 pieces of good news for you. The first one is that I'm going to share this spreadsheet for free because I want to share what I've learned and maybe help others reach their RC speedrun goals. Going forwards, we can work together to help improve the spreadsheet by sharing what we've measured. We can work out the unknowns and then include them into it. Secondly, I'm launching a crowdfunding project to raise funds for my Beast Car rebuild and 2025 Rosser campaign. I've got a shopping list of parts I need to rebuild the car, like parts for the steering mechanism and 4 new speed controllers. Any support towards that would be much appreciated. And to show my appreciation of people's backing, anyone donating £20 or over will have their name added to the car as it will be run at the Rosser 2025 events. The link for the spreadsheet will be on the crowdfunding page, which itself will be linked from the description below. Thanks for watching. Please like and subscribe and keep an eye out for my next video, which will start diving into electronic speed controllers in more detail and show how they actually work with my usual practical slant on things.